Well, today we would like to continue with what we have started, talking about the the mathematical models of systems. We said if we have physical systems such as circuits, we will be using KVL and KCL to model the system, to write the differential equation for the system. Okay, we will be also using Newton's law if we have a mechanical system. Okay. Before we continue, is there any question? Is there a question?
Yes, Doctor. In real life, in realistic models, it's not going to be clear, right? Using well-known formula like Newton's law or what have you, for example, in electric, the mathematical model can be very sophisticated and cannot be, for example, determined analytically, right? In some cases, yeah.
Well, look, okay, first of all, start from simple thing, which you can do. And then you are right, systems are complicated, okay? You will model each one of them and then interconnect them together. Large system, definitely, they are extremely complicated, okay? Sometimes, they call a system identification in which, you excite your system and collect the data, and from those you can identify what type of system you have. But
this is the numerical way, Dr. Iman, right?
This is numerical, yes, numerical model. It could be. But in general, look, what you will do, you start localizing from small pieces and then put them together. This is the way. Definitely, in classes, we are talking about something which is realistic. Simple to understand. But the whole process will be the same. It will be the same. It will be a little bit more complicated, greater, but the basic is the same. Suppose you have a huge network, okay? The network could be, you apply KVL, KCL several places in the network, and then you connect them together. So it is, the basic will remain the same. It doesn't change. A Newton's law for mechanical system, well, KVL, KCL for electrical system, for the circuit, they're not going to be changing. They are the same. They are the basic. Yes, it's true. Not only that, in real life, most of the time, you will have nonlinear system. And most of the time, we are talking about linear system, where linear system, the theory for linear system is well defined, okay? The analysis of linear system is well defined. If you want to analyze the stability of the system, we said, you look into the poles of the system, and if they are in the right half plane, you can say the system is stable. But if you have nonlinear system, you don't have the transfer function, because transfer function is defined for
the linear system.
Okay, right. So
and we'll have a chaos, and we have to deal with the chaos and
that's correct. So basically, now the question is, suppose I have nonlinear system, which is in general, most of the systems are nonlinear. What do you do to work to analyze the system?
We have to excite the system, for instance, or we have to, for example, use certain stability predefined.
No. You approximate the system. You linearize the system.
I see now. I see.
And then you study the behavioral system locally around the point of expansion.
I see now. I see. Yes.
Before we start, what's linear system? What is a linear system?
Linear system, we can define it mathematically. That is, we have, for example, y is equal, for example, to x, right?
Uh-huh.
when you multiply this by a factor, by a constant, for example, or we have studied this in 207. There is a way, a simple way to make sure that this is a
But you
linear
know, okay,
system.
okay. Let me give you suppose. Okay, suppose we have this is the x-axis, this is the y-axis. This is straight line. Is this system linear?
Yes.
Any other? How about the other, Shabab?
No.
Yes, it's linear.
Yes, and there is no. Who said no? Shabab, we have how many people we have in the class? I have, mashallah, 31. And I hear only 2 voices or 3. What happened to the rest? Shabab?
Yes, it is linear.
Volunteer. Is this linear or non-linear?
It's linear.
Linear relationship.
Linear. How many linear? No, this is not linear. If it is linear, okay, if it's linear, it should pass through the origin. Okay, this is a linear.
Yes, yes.
Okay, so back, okay, to the linear system, we can define it mathematically, but you have studied it in circuit 1 and circuit 2. Where come the concept of linearity in circuit 1 and circuit 2? You have studied it. Okay. Okay, look, suppose, Shabab, you have a circuit where you have 3 sources. Okay.
Mm-hmm.
How can we get the output of the overall thing? What do we do?
You use it as
Superposition.
superposition.
Exactly. Linear system.
Can be done by the superposition. Yeah. Yes.
Exactly. If superposition holds, it means that your system is linear. For Abdurrahman, what's your name?
Rahman.
Huh?
Abdurrahman.
Abdurrahman. What
No.
you're trying to tell me is the following. This is the definition. A linear system, if I have alpha x1 plus alpha 2 x2 equal to alpha 1 y of x1 plus alpha 2 y of x2.
Yeah, this is the homogeneity of the system.
Okay,
Yes.
this is what you were trying to tell me.
Yes.
Okay, now let's check why this is not linear.
Because B will, if we consider this
Because
kind
of
of
the
shift,
B.
B, yeah.
Because of the B. Because look, if let me use this one in here, basically. So I suppose alpha equal to 1 and y in this case equal, let's say, mx plus b. The equation for this one, mx plus b. So y of x1 plus x2 equal to what? Y of, okay, mx1 plus b plus x2, mx2, sorry. Look, this is x1, sorry, this is y1, but this is not y2. This is not equal to y2.
Right.
There is no b. If it's y2, it should be in this format. I should have the b. Okay, let me explain it again. Look, y equal to m, suppose x1, I have x1 plus x2, okay? Plus b, which is equal to what? mx1 plus mx2 plus b. This is y2, but this is not y1.
Yes. So y of x1 plus x2 is not equal to y of x1 plus y of x2.
Exactly.
In this case, alpha 1 and alpha 2 is 1, basically.
Exactly. So look, if b equal to 0, if this is 0, if this is equal to 0,
Then have shift.
this will be y2 and this will be y1.
I see. So we have a constant in the system, so it will not be linear. Yes.
Yeah,
No.
if you have,
Because the constant will be
if you have-
will yield delta in the in the response, I think, or something. I don't really.
Look, it is, as I said, if it is, linear system to start with, it should be degree 1. This is
Right.
x equal to 1. And on top of that, if it is linear, it should pass through the origin. Or, as I said, superposition should hold. If
Yes.
hold, then the system is linear.
Thank you, Doctor, for this.
Okay. So now, suppose I have no linear system. How do I?
Doctor, can you clear the board?
Can I clear it?
Yes.
Sure. Oh, sorry. What did I do now? Let me go back to
Slide 7.
okay. No. Okay. So suppose I have, as I said, principle of superposition will hold. Now, by the way, when I post the lecture, I post the slides as well as the video. So you can go back to the clean copy in the slide. Okay. Suppose I have no linear system. How do I linearize?
Taylor series, for example. First order expansion.
Taylor series. Okay. So basically, this is Taylor series. If you have f of x is nonlinear function, I linearize it around a point called the equilibrium point. Okay. Around A. Okay. So I will have f of A plus a prime of A evaluated at A over 1 factorial x minus A plus a double prime of A 2 factorial and so on. For a linear system, I will keep only this term and ignore all the other terms. This will be always 0 because look, this point, usually I do my expansion. Suppose I have f of x, x dot equal f of x. I expand this one around, the equilibrium point in which x dot equal to 0. So f of x at 0 at the point which I'm going to, by solving this equation, I will get, my point of the point in which I want to expand around. And in this case, okay, this will be 0, and I will keep only the first term. I ignore all the other terms. So what I will get a linear model. Of course, my linear model is valid around A. It's not valid everywhere. So it will be local. I'm localizing it.
Yes.
Okay. Well, this is basically what I'm saying. Suppose I have, this is dx dt, function of x, and this is the state, and u, and later on we'll be talking about those. But anyway, this is in general. If I have a nonlinear function, I can identify the nonlinearity, expand by using Taylor series, and truncate after the first order term. Let's take an example. This is the simple pendulum. Okay.
Sine theta will be approximated by theta, right?
Well, we will, first of all, we have a nonlinear system, and then we do the approximation. The concept is, how do I use whatever I have said, okay, to model the system? I would like to obtain the system model in here. Okay. Now, what are the forces acting on the system?
We have the gravity force, we have the tension.
This is for the weight and the tension. Okay. So.
And also we have, Doctor, like kind of a driving force, right?
What?
This is a driving force,
Yes, exactly. This is
or the system is naturally responsible.
these are the forces affecting the system. Now, in order, we have this mechanical system, and I want to write the differential equation for the system. So, since the motion in here, it's not linear, I mean, the motion is, you know, rotational, so I will be using what? Newton's law. But what law I will be using? I will be using the summation of the torque, okay, must be equal to the moment of inertia times the angular acceleration. So, first of all, let me decompose this one into two components. One component, okay, in the opposite direction of the tension, and the other is perpendicular to that one. So, if I decompose this one, this component will be mg cosine theta, while the other one is going to be mg sine theta. Any question here?
What did you do, Doctor?
Okay.
What did you do again?
What I'm, you know, if I have this force, I want to decompose this force into two components. I will take, this is my reference, the opposite direction of the tension, and the other one is perpendicular to it. So basically I have something like similar in this way. So,
Doctor, isn't it easier to make the ground reference?
it is easier to make what?
The ground reference, like separate the tension force
No,
into
no, no,
X and Y.
no, your reference from this point. This is the point of reference, not the ground. This is the point of reference. This is, if you go back to physics, I think, where did you take the simple pendulum?
Physics 101.
Physics 101.
Physics 101, go to Physics 101. So this is your reference. So if you decompose this one into two parts, this is going to be mg cosine theta, and this is mg sine theta. Look, this force, or the torque in here, will be in opposite direction of the tension, so they'll cancel each other, and there is no motion in that direction. The motion will be in this direction. Okay, now, this is m, and I need the moment of inertia. What's the moment of inertia for this system? The moment of inertia, okay, for a point mass is simply the mass times the square of the perpendicular distance to the axis of rotation. You can think about it in here as, you know, we are talking about a force, I mean a torque. So J will be L square M. How about the torque in here? What is the torque in here? What does it equal to? The torque equal to what? With respect to this point, it's equal to the force, which is mg sine theta, times L. So this is basically what I'm saying. L times the force will give you the torque. This is the only torque which we have in this direction. Assuming that there is, you know, there is no friction. I'm assuming, you know, I'm neglecting anything else. This must be ml square alpha. What's alpha in terms of theta? What's alpha in terms of theta? Remember, alpha is the angular acceleration. Theta is a position.
Is it represented in the second derivative?
Exactly. Exactly. It's second derivative of theta. So, first of all, I eliminate, and I get alpha equal G over L, which both of them constant, sine theta. And this is my differential equation. It is nonlinear because of the sign. Okay, This is nonlinear differential equation because of the sign. Now I can linearize by using Taylor series around the zero. I will expand around the zero. Okay. So if I want, what is the sign? What is the Taylor series expansion of the sign?
Theta. Theta.
It's going to be d second theta dt square equal g over L theta.
No, this is a separable differential equation.
Just 1 second. Let me, okay. Let's do it in here. Okay. F of x or f of theta equal to sine theta. I'm expanding around zero. So f of theta equal f of 0 plus f prime of 0 over 1 factorial theta minus a equal to 0, so theta, plus the other terms. What's f of 0? What's signs of 0?
0.
0. Plus derivative of the sine theta.
Cosine theta.
Cosine, evaluate at 0.
1.
1. So this will be theta.
theta.
I ignore the higher order term because I don't want I want to keep only the linear term, so which is equal to theta. I want to keep only the linear term. Any question?
Where did the G over L go, Doctor?
How did I?
It was sine theta J over L.
Yes. Those are constant. I don't care about.
طبعا دكتور هنا for this approximation theta has to be very small, right?
Exactly. That's what I'm saying. Usually the expansion. Okay, let me clear okay. Yes, that's what I said at the beginning. You know, the model is valid around the expansion point of expansion. In this case, I'm expanding around the zero. Within let's say
30 degrees.
Certain very small range, that will be that will be perfect. Otherwise, for example, if you want to sine, let's say sine usually sine theta equal theta if you take theta in radian approximately. Okay. Now, for example, if theta is let's say 0.1, sine 0.1 will be sine of 0.1 radian. It will be okay 0.1. But if you go, let's say the 45, which is pi over 4, definitely you are not going to get the answer will be is not accurate at all. So yes, that's why the linear model is valid for certain point. Sometimes look, you can expand around several points of equilibrium points, and for each point you will have a model, and you can design a controller, let's say, for each model. Generally speaking, I mean, the linear, it's true, it's approximating the nonlinear, but within certain range. Even if you go to the electronics, I think they talk about small signal model, or what do they call it?
Yes, a small signal.
Yes. So basically, it's always, when we talk about linear approximation, it means that we are expanding around certain range. Beyond that one, definitely the approximation. It's approximation. The approximation will not be valid. Okay. Any other question?
Yes, دكتور عندي شوية confusion. الديفرنشال equation كتبتها G over L theta.
كيف؟
في السلايدات مكتوب G over L theta.
Yes. G over L. Yeah, because look what I did in here. Look, this is what you have. Alpha equal G over L sine theta. D second theta dt square equal G over L. G and L, they are constant. So in the constant, you don't care. You just multiply by the constant. So basically, you expand this one. Okay, you expand the sign and multiply by the constant. The constant will not affect you.
Oh, so this is the approximation.
Yes. No, this
okay.
this is constant.
No, I mean the one under is the approximation.
Okay. No, the constant will be out. You just multiply. You, I mean, you in here again. There's some note. I think it said, okay, identify the function responsible for nonlinearity. Okay, expand, and then multiply by the constant. That's constant, which is it has nothing. I mean, you just multiply by it. Okay.
This is good. Thank you.
The minus sign.
Any other question?
Yeah, the minus sign, Doctor.
Okay. Minus sign, look, because in here, this is going to be what will happen. It will go in this direction and swing back. Okay. So you can model it. Yeah, you can think about it and you can write. But this is the simple pendulum. It will going back and forth because you are having certain energy in here and it will go. Think about it if this is the positive direction or negative direction. Okay, you could think about it. This is moving in the negative direction, but later on it will come to the positive. So usually we don't, I mean, the direction sometimes, it is little, yeah. The minus sign you mean in here, which I put in here. Okay, as I said, minus sign, there will be sometimes minus sign because of the direction. But if you, as I said, suppose you are in the at this point. In here, suppose you are. Okay. So you'll move back, isn't it? So one of them positive, the other one is going to be negative. Assume that this is the positive.
So we always ignore the minus sign?
You ignore it, yes, in a way, yes.
ولأنه دكتور أصلا بيصير هو ماينس والتسارع بعد التسارع ماينس يعني الأكسلريشن angular acceleration will be minus so minus والminus will cancel.
The acceleration will be in the minus.
Because it's acceleration is nothing but a vector quantity.
Wait, if you are moving in the direction, you are accelerating, and here you are stopping, so zero. So it will accelerate in this direction. No.
Yeah, the acceleration is a vector quantity, so it will be minus. Not expressing whether it will increase or decrease.
But look. Anyway, I'm not going to go in that much of
physics
of it. I just want to point out, okay, you could have a nonlinear, and this is the way to do it. The simple pendulum, it is, it is in Physics 101. I think in your text also, in your textbook, they put it, if I'm not mistaken.
I think this is the typical example in any nonlinear course.
Yes. Okay, now let's move into the Laplace transform. The definition of the Laplace. I'm not going to go over the Laplace transform. I just put in here the definition for the Laplace transform. If I have a function f of t, how do I get the Laplace transform of that function? That basically I will integrate from 0 to infinity of the function, multiply by e to the power minus st dt, and then we'll get the transfer function. Now, what's important, if I have f of t will give me f of s. What is the Laplace transform of d f of t dt? What does that say?
S of S.
Minus
S0.
f of 0. Okay.
Yes.
Okay.
F small, Doctor, or?
Yes, small. Yes, small. F small, not the large. Yes, f of t, because the initial condition associated with the t, not with the s. Okay. So this is basically what I'm saying. This is what I'm saying. Okay. This is in general. If you have an integrator, then you will replace it by 1 over s. Well, let's talk about the transfer function. I assume, okay, I will give you a homework. The homework will be, how do you go back and forth between, the time domain and the S domain. But as I said, I assume that you already covered this material in 207. I'm sure it's well covered in there, and there is no need for us to, repeat it in here. Now let's talk about the transfer function. If you remember the transfer function, if I have, let's say this is a box where the transfer function for this system is defined as the ratio of the output to the input, setting all the initial condition to 0. Okay, so in the transfer function model, we are assuming now. By the way, the transfer function, again, we are not saying it, but the transfer function of linear systems. If you have nonlinear system, there, transfer function will not be defined. It's not defined for, there is no transfer function for nonlinear system. Okay. So suppose I have this example. What is, okay, y of s over r of s. Find y of s over r of s. Can you tell me how do we proceed?
We write the differential equation, then we do Laplace transform.
Okay. We already, in the last lecture, we already have that one.
Yes.
This is what we have in the last lecture. The differential equation for the system, okay, is given in this format. Now, by taking the Laplace transform of both sides and setting the initial condition to 0, I can get the transfer function. So,
Right.
okay, so let me take, okay, this.
Doctor, I just have one question.
Fadal.
How did we get d double prime y over dt square?
How do I find this one?
Yeah.
Did you attend last lecture?
Yeah, I attended, but I didn't get it.
Well, basically, okay. Look at here again. This is M, the free body diagram. Let's try it. What are the forces in here? What are the forces?
R of t.
R, okay, of t. This is the one which I'm pulling, and this is my point of reference. This is Y. What else I have?
Friction.
I have the friction, which will go in opposite direction.
Yeah, and spring.
Which is, well, we said the force due to the friction will be B, the constant of friction, times the y dot, speed. And also we have the spring itself. This is K times X, or time Y, sorry. Okay, now write, Newton's law. And Newton's law will be the summation of the forces must be times m times the acceleration.
No, I get it now.
Okay, the force is equal to R minus, okay, minus this one equal, so R minus xy minus by dot equal m y double dot, the acceleration, which is this one.
Yeah.
Okay.
Yes.
Now, as I said, each derivative in the transform domain will be replaced by S if the initial conditions are 0. And that's basically, we are doing transfer function, so we set the initial condition to 0. So what do I have in here? What is the first one? Will be give me m what?
S squared.
S squared.
S squared y of s plus bs y of s plus k
y of s
equal to r of s.
Divide. Now take y of s.
So y of s over u of s, which is basically transfer function, 1 over m s squared plus b s plus k.
Then we find the zeros and the poles, right?
Yes, but you know, at least okay. For the time being, let's focus on the transfer function. This is transfer function.
Okay.
So look, in here, I have the differential equation model and the transfer function model. Are they related?
Yes, of course.
Yes.
Okay. Take the Laplace transform from here, come, and that will give you transfer function. And set all the initial conditions to 0 and take the ratio of the output to the input. How about if I want to go back?
You need inverse Laplace
Inverse Laplace.
transform.
Reverse, okay. Replace each s by a derivative. And you get the differential equation. So basically, if you remember at the beginning of the last lecture, we said, okay, we will have different models. One of them, we start with differential equation, and then the transfer function, and they are related. Okay? If I get one, I can get the other. Any question here?
But doctor, going from Laplace to the differential equation, it's
Yes.
sometimes it's tedious because you know the inverse Laplace. It's a the definition of the inverse Laplace transform is not.
No, wait. No. I'm not saying, okay, no. You are not inverting anything. What I'm saying, if you have this one, how do you get the differential equation? Cross multiply. So what do you get?
You mean the just
Square y of s plus bs y of s plus k y of s equal r of s.
Yes.
To the time domain, replace each s by a derivative. So this is going to be m y double dot plus b y dot plus k y of t equal r of t. That's all. That's what I'm saying. We don't know. I'm not asking you to, get me. You are talking about response or something. I mean,
Impulse response. Yeah.
simply in here, replace each, differential, each s by a derivative. Okay, and this is basically, so they are related, as I said. The differential equation model and the transfer function model, they are related. You can go back and forth between them. Let's take another example. Suppose I have this circuit. Now, how do I find the transfer function?
ABL.
Use voltage division.
Okay.
You want V2 over V1, right?
So basically, what you are saying, I will write the differential equation for the system, or we know the impedance in here.
1 over SC.
So R, this is V1. Okay, this is 1 over CS.
Yes. Voltage divider rule.
So voltage dividing rule. So basically, I will have V2 of S equal to what?
1 over CS all over 1 over CS plus R.
Over 1 plus, sorry, R
Plus 1 over CS.
CS V1.
Yes.
Which is equal, if I clear the fraction, I will 1 over R CS plus 1. Okay.
V1.
V1, or the transfer function V2 to V1 equal to 1 over R CS plus, and this is my transfer function. So either, and that we have in the electrical engineering, in circuits, we work on the impedance in the transform domain rather than, putting it in the time domain and get the transfer function. Or you can write the differential equation again, and then from differential equation, you can proceed. Okay? Any question here? Well, in here, the only thing in here we add, you can define RC at the time constant of the circuit, and you replace it by tau. So the transfer function, okay, of the system is the ratio of the output to the input, okay, and it's written in a polynomial in the numerator and polynomial in the denominator. Now we are introducing a new definition. Okay, the system is called proper if m greater than or equal to m, and the degree of the denominator greater than or equal to the degree of the numerator. If this is the case, we call the system proper. Otherwise, the system is improper. That's basically if the degree of the numerator greater than the degree of the denominator, the system become improper. We will be working in this course with the proper system only. Okay. Physically, if you are talking about the time domain, it means that in proper system, you will have the derivative of the, inputs is greater than the derivative of the outputs, which we are not going to work in this course. Well,
Doctor,
yes.
I'm gonna ask another question.
Us?
Oh yeah, after. Sorry.
دكتور عندي سؤال.
تفضل.
For the transfer function, why is the initial conditions are zeros?
Well, this is the way, okay, this is the way, this is the way they define transfer function. This is the way they derive it, okay? That's why, okay, look, this model, later on we are going to have another model called state space model.
في الكورس هذا ولا في الكورس ثاني؟
كيف؟
في الكورس هذا.
بالكورس هذا.
ايوه.
The state space model يكون more general than transfer function model because of, one of the reasons for it is in here, I am, losing some information. I'm setting the initial condition to 0. So suppose I have a system in which there is an initial condition. What do I do?
And I don't consider, Doctor, the past state of the system.
You consider what?
In the transfer function, we don't consider the past state of the system. We don't really consider, take care of.
Okay, suppose you have initial condition.
So of course, this model will fail.
Yeah, it is a model. Look, this model is defined in this way. This model is very powerful model, but we are going to see later when we go to the state space model, we will see sometimes this model will not give you, good information about the system. One of them is this, the other one, there will be a possibility of pole zero cancellation. And, when we go to stability, as a matter of fact, it's quite possible that, you will be deceived. That basically, I don't want to go in that, but anyway, okay, suppose I have 1 over S minus 1. Is this system stable or unstable?
Unstable.
Unstable because of the S in here. So I have, okay, S minus 1, S plus 1. So now, from this point to this point, what's the transfer function?
1 over S plus 1.
1 over S plus 1.
So, which is stable.
Stable.
Okay. Suppose you are doing this in the lab. If you are working with this system in the lab, after a certain time, your system will be either burn or it will saturate, and you will not get what you want because something is hidden. The pole and zero, there was certain cancellation. So look, why the initial condition is 0? This is the way they define this model. The model is very powerful, but it has, with its advantage, it has also drawback from it. So for the transfer function model, this is the way it's been, defined. The transfer function is function of the system itself. It has nothing to do with the input, even though we are taking the ratio of the output to the input, but it is function of the system itself. It's not function of the, it is not function of the input or the output. We will be using transfer function stability and so on. Now, suppose I have the system, okay? How do you define the pole of a system? What's the pole of a system?
Zeros of the denominator.
The pole of the zeros of the denominator, yes. Or the pole is defined as the frequency at which the system becomes infinite.
Right.
If?
I said right.
Yes. S, let's say S plus 2, S plus 1. If I excite the system at S equal to minus 1, the ratio is going to be infinity. So this is the way to define it. Or, as you said, it is the roots of the polynomial denominator.
Sure.
Yes.
When we say frequency, do we mean that the system is kind of oscillatory? Because, kind of frequency is something that
say that
is
again.
repeating.
Wait.
When we say a frequency, it is the
Uh-huh.
frequency at which system becomes infinite. Do we mean that the system motion is oscillatory motion? Because frequency means that it's repeating itself with a certain
Not
frequency.
necessarily. Not necessarily.
Yes.
This will be S squared plus 1. This is oscillatory. This is because the poles are in here. But if my poles in here, the response is going to be, it's oscillatory, but it's a growing oscillation.
I see.
Okay, so it is not. So anyway, now, while the zero of the zero is the frequency at which the system become, zero, or the roots of the numerator. Let me, okay, if you want to represent the zeros and the pole on the S plane, we represent the pole by X and the zero by a circle. For example, if I have S plus 1, S plus 2, S plus 3, basically I will represent them. I will have two poles in here and 1 0. This is the way I represent my poles and zero in the S plane. Okay, the system order is basically the degree of the polynomial in the denominator. Okay, let's take the following example. Is this system proper or improper?
Proper.
Okay, and what are the pole of the system?
0 and negative 2.
minus 2.
0 and minus 2.
Okay, what about the system order?
2.
Second order.
Second order.
Okay, now let's take this one, the last one.
Improper.
This is improper because the degree of the numerator is greater than the degree of the denominator. And the order will be, what's the order? System order.
Will be
First degree order.
First degree.
It will be first degree. Okay.
Doctor, again, sorry, is it proper or improper?
Which one?
First one.
Which system? And this is improper still, because the degree in the numerator second and the first. So the degree of numerator greater than degree of denominator, which is improper.
Doctor,
Okay.
can we say that 0 is a pole in this case, or because it cancels, we will not consider it as a pole?
If you cancel, no. If you cancel it, yeah, it's not a pole. Look, sometimes okay, the pole 0 cancellation. If it's unstable, it creates problem. But yeah, in general speaking, yes, we do cancel them. But the order of the system is still, I mean, yeah, definitely the order of the system will be reduced after the cancellation. Is that
So we
that's
don't consider zero as a bool in this for
If?
that matter. We don't consider zero as a bool for that matter.
Exactly, exactly. You are right. You are right. Okay, look, quickly, what I want to do, I want to stay, a couple of minutes in here. I can do it by using MATLAB. I can find the transform of a given function time domain. To do that, first of all, I define in MATLAB, I define SYMS. It define the symbols T and S are symbols. They are symbols. They are variables. So if I have a function, given function in the time domain, I can use this command. F Laplace of F, T, and S, it will give me the Laplace transform. For example, if I have this function, okay, what I will do, I define the system S, Y, M, S, T, and S that define my variable, write the function, and then use the command. It will give you the Laplace transform of this function. This is rough mode. It will take the Laplace transform of the first one, second, third. In general, okay, you can simplify by another command called simplify F. And finally, if you say pretty, it will give you the Laplace transform in, a nice format, in very nice format. You can also go back if you have the Laplace of a function. You can go back to the function by using another command called iLaplace. Okay. You can use a command called iLaplace to go back from the S domain to the time domain. This is very, powerful. It will help you if you have a complicated function. You can use MATLAB to find the transform for you. Okay, a little bit. Is there any question before we stop?
Yes, Doctor, you mentioned something about the homework. You will post it today, inshallah.
No, the homework this week, we are giving you, we are letting you relax this week. Inshallah, you will have it next week. Next week, we will